College Algebra Chapter 3, Section 8, Polynomial Equations and Inequalities, Further Applications and Models. Some methods for solving quadratic equations were known to ancient civilizations. The 16th century mathematicians derived formulas to solve third and fourth degree equations. And then in 1824, a Norwegian mathematician by the name of Niels Henrik Abel proved it impossible to find a formula to solve fifth degree equations. Now that doesn't mean they were unsolvable, it's just that there was not a formula that could be found like the quadratic formula that could deal with fifth degree equations. Now the formulas for third and fourth degree equations are extremely complicated, so we don't learn those. The one formula we do learn is the quadratic equation. It's also true for equations of degree greater than 5 that there is no formula that you can come up with that will solve them. Okay, here's our first try at solving a higher degree equation. Why don't you pause the recording to try this? Before you do that though, let me tell you that you're going to be factoring this by grouping. See if you can remember how to do that. Pause the recording, give it a try, and resume to check your answer. Factoring by grouping is exactly what it says. You're going to factor by splitting the equation into two groups. So x cubed plus 3x squared becomes one group, and minus 4x minus 12 becomes our second group. Then what we do is we factor the common factor out of each group. So for x cubed plus 3x squared, we're going to pull out x squared, which leaves us with x plus 3 in parentheses. For the minus 4x minus 12, anytime you have a minus in front of that first term, you want to pull the minus out with whatever you're going to factor out. 4 is the common factor here, so we will factor out the minus 4 and be left with x plus 3. Notice now we have both parts with a factor of x plus 3. So x plus 3 becomes our common factor. We pull it out in front, and then we write down what's left. And what's left after you pull out x plus 3 is x squared minus 4. Now, as long as you still have a square term, you want to ask yourself, can it still be factored? And the answer here is yes. X squared minus 4 is the difference of two squares and splits into x minus 2 times x plus 2. Set each of these equal to 0, and we get three roots, negative 3, positive 2, and negative 2. And we also can solve polynomials if they're what we call quadratic in form. An equation is quadratic in form if it can be written as au squared plus bu plus c equals 0, where a is not equal to 0 and u is an algebraic expression. Now, some people have a hard time dealing with this when they actually replace the x squared with a u, so you don't necessarily have to do it this way. It's just one way that you can think about it. So let's look at what this is going to be like. We actually have done these before also. Why don't you pause the recording and give this a try and resume the recording to check your answer. Okay, so what they do is they actually replace, instead of u, which they said to do, they're actually replacing it with t. But they say, hey, look, x to the fourth is the same as x squared squared. So we're going to let x squared be t. So we're going to replace all of our x squares with the letter t. So that changes our quadratic, it changes it into a quadratic, so we have t squared minus 6t minus 40 equals 0. And then we factor that into t minus 10 times t plus 4. And then we solve that, and we get t equals 10 or t equals negative 4. But then we say, oh, wait a minute, we didn't start with a t, we can't finish with a t. So we replace t with x squared, because that's what we defined it as. So we have x squared equals 10, or x squared equals negative 4. Then we solve for x. So x equals plus or minus the square root of 10, or x equals plus or minus 2i, because the square root of negative 4 is 2i. And that's our solution set. Now again, if substituting the t in for x squared messes you up, you can just kind of think of it like, okay, instead of x squared, I have x to the fourth. So when I factor, instead of x minus 10x plus 4, it'll be x squared minus 10 times x squared plus 4. And that works a lot better for some people. You use whichever method you're most comfortable with and makes most sense to you. Here's another example. This time we're going to show that 2 is a solution of the polynomial x to the third plus 3x squared minus 11x plus 2 equals 0, and we are going to find all the rest of the solutions also. Let me give you a hint. We're going to start with synthetic division to show that 2 actually is a solution. Pause the recording, give this a try, and resume the recording to check your answer. All right, so we used synthetic division and divided out the 2 and saw that it did indeed work. And we end up with 1x squared plus 5x minus 1. And then what we're going to do after that is we are going to solve that x squared plus 5x minus 1 equals 0. We're going to do that using the quadratic formula because it will not factor. And when we use the quadratic formula, we end up with negative 5 plus or minus the square root of 29 over 2. So our solution is negative 5 minus square root of 29 over 2, negative 5 plus the square root of 29 over 2, and 2. You can also use graphical methods to solve a polynomial equation. So we're going to use our graphing calculators to put in this polynomial, 2.45x to the third minus 3.14x squared minus 6.99x plus 2.58. We're going to use the graph of that to figure out where p of x equals 0, where it's greater than 0 and less than 0. Pause the recording, give this a try, and resume the recording to check your answer. Okay, here's our solution. Looking at the graph and using the calc function of calculating zeros on our graphing calculator, we find that the x-intercepts are at approximately negative 1.37, 0.33, and 2.32. So p of x equals 0 at those 3 places. Now looking at the graph, we can see that it's above the x-axis, in other words, positive in between negative 1.37 and 0.33. And then again, after it crosses at 2.32. So from 2.32 to infinity, it's also positive. And then it's negative from negative infinity to negative 1.37, where it's below the x-axis. And then it's below the x-axis again from 0.33 to 2.32. Now, if n is a positive integer, k a non-zero complex number, then a solution of x to the n equals k is called an nth root of k. For example, negative 2i and 2i are square roots of negative 4 because when you square both of those, you get negative 4. Negative 2 and positive 2 are sixth roots of 64 because when you raise them to the sixth power, you get 64. So we have a theorem now. It says that if n is a positive integer and k is a non-zero complex number, then the equation x to the n equals k has exactly n complex roots. We're going to find all 6 complex sixth roots of 64. These will be both real and imaginary. What we're going to do is I'm going to walk you through this. This is going to involve some factoring that we haven't done in a while, since last year anyway, so may need a little bit of a reminder. To do this, we're going to solve x to the 6th equals 64. And the first thing we're going to do, as with any polynomial, is get it equal to 0. So we subtract 64 from both sides. Now, x to the 6th minus 64, believe it or not, is a difference of 2 squares. It's x to the 3rd times x to the 3rd, and negative 8 times 8. So we split it up, x to the 3rd minus 8 times x to the 3rd plus 8. Now here's the factoring we haven't done in a while, and that is factoring the sum and difference of 2 cubes. What you do is you take the cube root of the first term and the second term. So we're going to use x and 2. The first 2 parentheses here are how you factor x to the 3rd minus 8. Notice the pattern. It's x minus 2, 2 is the cube root of 8, times x squared times 2x plus 4. 4 is minus 2 squared. It's 2 squared. So that's where we get that from. So x minus 2, x squared plus 2x plus 4. Now we're going to do the same thing to x cubed plus 8. And notice that the numbers and the terms are all the same here. It's just the signs are a little different. Because when you have a sum of two cubes, the signs go plus, minus, plus. So it's x plus 2, x squared minus 2x plus 4. Now, we've still got two parentheses that have an x squared involved. So first of all, x minus 2 gives us 2, and x plus 2 gives us negative 2. What we have to do with the x squared plus 2x plus 4 and the x squared minus 2x plus 4 is that we have to use the quadratic formula on them. And when we do that, we get negative 1 plus or minus I squared root of 3, and positive 1 plus or minus I squared of 3. So those two each are two roots, and then we have the two real roots. All right, now for a little application problem. We have a box with an open top, and we're going to make it from a rectangular 12 by 20 inch piece of cardboard. We're going to do this by cutting equal size squares from each corner and folding up the sides. Now we've done this before where we knew the size of those squares. This time we don't, so we're going to have to use an X for those. Let's see. A, if x represents the length of the size of each square, determine a function v that describes the volume of the box in terms of x. Determine the value x for which the volume of the box is maximized, and what is that maximum volume. So you're going to find the x and the y for that. And here we have a little diagram, so you can see how everything fits together. The outer dimensions of the cardboard are 20 by 12, but we're going to cut x from each corner. And that's going to leave us with the bottom of our box actually having a dimension of 20 minus 2x and 12 minus 2x. That's going to be our length and width. Our height of our box is going to be x. Now, knowing that, see if you can find that function and see if you can go ahead and find the maximum volume. Why don't you pause the recording, give it a go, and resume the recording to check your answer. And here's our solution. The volume obviously is length times width times height, which means we have to multiply 20 minus 2x times 12 minus 2x times x. When we do that, we get 4x to the third minus 64x squared plus 240x. And x has to be between 0 and 6. And the reason for that is that our dimensions must be greater than 0, and that's only going to happen for all three dimensions when x is between 0 and 6. And then we're going to use the graph of v to find the local maximum. So we graphed our volume, and then we're going to use that graph to find the maximum point. And we're going to do that by using the calculate maximum function on our graphing calculator that you can find in the calc menu by hitting second trace, then going to maximum. Remember, it's going to ask you to give it a left bound, a right bound, and then a guess. You must complete all three parts of this to actually get the maximum. You'll know you've done it when you see the word maximum at the bottom of the screen. Notice it's giving us the x, 2.427, or 2.43, and y is going to be our volume, 262.68 cubic inches. This recording is extra practice. Pause the recording between each problem to give it a try and resume the recording to check your answer.